Okay, so it is time now to move and take a plunge into the first modality that we want to cover, which is going to be projection radiography. So, like I said, whatever we have covered so far, we have covered the physics, mostly of X-ray physics, right? But I also warned you that if you take just the interactions of photons, even if it is higher energy, the interactions are similar, and therefore, when we get to PET and SPEC, the nuclear medicine, we will only have a cursory review and some aspects that are speciality to radioactivity that we ignored so far, that will be covered there. Otherwise, the style of coverage is going to be, we covered the X-ray based physics so far. Now we will start with projection radiography and subsequently X-ray CT. So these two we will cover. So we had the physics, then how are we planning to cover it? Oh, from physics we want to go to instrumentation. From instrumentation we want to go to image formation. From image formation we want to go to image quality. Okay. So with that we will start projection radiography. By now you should be able to understand technically what is meant by projection radiography. Projection is collapsing the dimension, right? So in our case we are going to talk about a 3D volume that is collapsed, that is projected to a 2D plane. That is what we call as projection radiography. So now you know what is ionizing radiation, right? So we want to talk about projection. Radiography is an image drawing, right? So in projection radiography we are going to talk about X-ray projection radiography. We say projection radiography, but what is meant here, what it implies is we are going to talk about X-ray projection radiography. That is what happens if I send X-rays through this 3D volume. How can I project this onto the 2D, get a graph of based on the radiation that we are sending in. So immediately when we talk about it, we have used several examples. So what is going to be our goal here? Our goal is not going to be cover one particular system application. Our goal is to cover the underlying concept, the underlying instrumentation that is there, that exploits the first principles of the interaction that we talked about, the physics that we understood. So immediately when we say what are the examples, you would have probably heard say chest X-ray, which is an example that I kind of used very routinely, because likelihood that you would have seen that system, you would have been part of the imaging process, you would have taken a chest X-ray at some point of time. But that is one of the predominant ones that you may be able to relate. But is there others that ring a bell to you? Have you know the other very commonly used systems? So this is very wide ranging. Each one is specific depending on the context, but all of them are having the same underlying principle that it is exploiting, which is what we will cover here, right? So chest X-ray, then mammography, right? At least women, now there's a lot more awareness, right, for women breast cancer. So do mammography. So you would have been hearing that term. Even though it doesn't say it is X-ray based, you would have heard it as mammography. But essentially it is, it's a projection X-ray modality. Then angio, right, you would have heard this term angio, heart. They want to see the vessel, so there is a block. They do why don't you do a angiography, right? So that also, of course, there are CT versions of it, but essentially it is also exploiting projection radiography also is there for quick view. Then, so cardio, cancer, right, breast mammography, lung infection, all of these are very common, you would have heard, okay. Of course, there is fluoroscopy, that is also very common. So what is the commonality? When we say X-ray projection radiography systems, all of this, the output is an image, okay. So what are the properties? Well, there are different aspects, right? When we talked about properties, as in what are the common underlying features of these systems, right? We talked about some image quality aspect, some radiation, safety aspect, right? Those are the general requirements. If you review our introduction, general requirements, we did give out some certain common general requirements irrespective of the medical imaging modality. So, here we want to be more specific about X-ray projection radiography system. What are the general properties of that? It has good resolution, in fact high resolution. This is something that we covered just recently with respect to dose. So, you have to have low dose, you cannot dose the patient to get good image quality, right. So, low dose. So, what is the idea of what does this low represent? We are talking about 30 millirads, right. So, which is essentially about 1/10 of your annual background exposure that you anyway get. So, it's not. So, the cost of doing this imaging, right, is way less compared to the benefit that you derive. Cost could be safety issue, not the rupees or dollars, right. So, low dose. So, low dose is good, right. Then large coverage area. What do we mean by example of chest X-ray? A standard chest X-ray has this, right. You would have seen your doctor put it under the light and see and tell. So, there is a common size that it comes, right. So, you are able to take one shot of the chest. So, it is a large coverage area. I mean, it is all relative. It is not whole body, but it is still significant portion that you can get with a very short exposure, 0.1 second. So, that is why I said when you go to if you had been to a typical chest X-ray, there is more time spent to make you stand in position, and he will ask you, instruct, don't stay still and all the other things. The actual imaging, after the technician goes to his room and says done, right. I mean, it's like that. So, it's so instantaneous. So, 0.1 second is actually the exposure. You probably know what it means, right. You send the X-rays through, it goes through the body, comes to the other side, it gets detected. How much X radiation you are exposed to, right. The ionizing capability is very small. You are sending it only for 0.1 second. So, in that sense, it is quick, right. So, these are the desirable properties. Only disadvantages is projection. What do we mean by projection? Your depth resolution is lost. Now I use this term, hopefully you are able to recognize. Depth resolution is lost. What does it mean? Oh, resolution. Resolution is nothing but how am I able to resolve two objects, right. We talked about temporal resolution, spectral resolution, spatial resolution. This is spatial resolution but on the third dimension, which is your depth. So, in projection radiography, your depth resolution is lost. What does it mean? Oh, I cannot tell the separation between the front and the back because I am collapsing the dimension into the plane of the wall. So, that is a disadvantage. Despite that, because of the other desirable features that you see here, properties, this is a staple. It is heavily used, right. Very limited applications are actually listed here. I mean, I am sure one of the other things that you are very familiar, you break a bone or you suspect breaking a bone, a quick thing is they will ask you to go for an X-ray, right. Then that can tell whether you have a fracture or not. So, these are very commonly used applications. So, it is important we need to not worry too much about the customization for application, but there is a common instrumentation that goes behind these systems. So, that is what we will. What is a common instrumentation? What does it capture of the physics? Then the imaging, and then the quality aspects, combining the physics and the imaging equations. How does the quality? Okay. So, we will get into projection radiography instrumentation first. Later, we will do image formation. After we do the image formation, we will talk about image quality. So, within instrumentation as well, we will cover only the generic instrumentation. We will not really cover the custom, like if mammography, there are certain customizations that are done. If it is chest X-ray, it is something else. So, we will not worry about the fine tuning. We will cover about the major instrumentation components. So, you have your X-ray tube, you have some filtration restrictions, compensation contrast agents, and then film screen detector. In fact, we will do film screen detector. Digital X-ray is something that is now very common, and therefore, we will attempt to cover this if time permits. Okay. Image formation. So, we will get to that when we get to image formation. Finally, image quality. All of these terms you would have seen, okay, but we will get to that when we complete these. So, let us take a jump into the instrumentation. So, when I talk about instrumentation, what instrumentation I am talking about? I am talking about the imaging system instrumentation. System is the complete part. What do I mean by complete part? In our case, we are going to have a source that is generating the X-ray, and then a patient is standing or lying or whatever. But then we are talking about through transmission. So, there is a source which generates X-ray. X-ray is sent into the body, and we will have to have a detection behind the body. So, it is going through the body. So, this is a through transmission setup that we are going to cover. Okay. So, that means what are the basic components? A general sketch, you should have a source side, you have a patient, you should have the detector side. These are the basic big picture, right. So, you will have the source side, you will have the patient, and then the detector side. So, this is a through transmission setup. Okay. So, now what we will do is we will cover in the same order. At least we will talk about the source first, and then about whatever you see here, right, some add-ons, and then we will in fact talk the imaging aspect we will cover later. But from an instrumentation point of view, is there something to instrument in a patient, right, or to do with the patient, based on the patient, that we will cover. And then of course, we will talk about the detector side of it. So, this is the order in which we will go. So, let us start with the X-ray tube. In fact, with X-ray tube, right, given that we covered the physics already, a sketch alone tells what it is supposed to do. Okay, a sketch here, and of course, a photography. This is a photo of a typical X-ray tube. Just for that, you can appreciate that it is having a glass housing, so you can see what is there inside, right. The details of which are captured here. Okay, so what do you see? The moment you say X-ray tube configuration, get back to your physics when we talked about electromagnetic, ionizing radiation, particulate interactions. We talked about, we are interested in using this particulate, right, to generate X-ray in X-ray tube. So, we gave already some hints about the working principle of X-ray tube. What you see here is a more detailed version of how that is executed. Okay. So, if you recall, what we talked about that time is we just said, there is this particulate, specific particulate that we were interested in electron. So, you have an electron, that electron is accelerated across with a voltage drop, and it hits the anode, and you have all these radiative collision, right. Remember all the physics of interaction of particulate with material that we covered. Fine, that is what is the big picture. So, now the question is, okay, where did this electron come from, right? You said, we accelerate this electron, and we defined kilo electron volt, right. So, we had electron that is going, the kinetic energy is getting deposited there. So, half mv square, all this we did. So, where does this electron come from? See, that is a detail, right, and that comes from here. You have what we call as a filament circuit. What is a filament circuit? So, this is the cathode assembly. So, on this side. So, essentially this filament circuit helps you to create the electrons, generate the electrons. Then you have some details here, right. So, once the electron is generated, you still see some C kind of structure here. essentially that is trying to focus, right? So you don't want the electron to go everywhere. You want to channel the electron so that it goes and hits the anode. This we studied. Once the kinetic energy, after it's accelerated, it interacts with the material, radiative, collision, all this we Bremsstrahlung, that we covered. So here there are two pieces of interest. One is the filament circuit that is going to help you create the electrons. Electron cloud is going to be created, and of course there is this focusing part which is going to keep the electrons ready so that it can go directly hit the anode at a desired location. Okay, so that was one detail. The second detail, we said it, but we'll flesh it. So electrons are available here. So the moment you apply a voltage, right, the electrons will move. That's what, that part we covered. But what we did not cover is, we have radiative and right? We talked about heating, Bremsstrahlung, right? So here we just that time told there is an anode, but you see there is an anode assembly. Okay, so we need to shed some light on what is there and why it is there. High voltage is not a big deal. We talked about, we are going to supply high voltage to this anode. That potential drop is going to make this electron, right, move and attain kinetic energy and hit, right. So this schematic vividly represents what are the components that are there in the X-ray tube, and broadly you have three aspects. One is the cathode assembly, the other is the material itself where the physics happens to create X-ray, and then the anode assembly that makes sure that the tube is usable and this can be reliably produced. The interactions can be controlled. Okay. Of course, there is a glass housing so that it is easy to handle, and it does some role in some of the aspects of filtering that we will talk about. So the filament, right, the filament circuit that I talked about, what does it do? It controls essentially the tube current. So you have an X-ray tube, so there is a current that is flowing through, right? You have the electrons, and the electrons are going to flow across a voltage, so there is a current. So the filament that is there does two things. I mean, essentially it controls the tube current, but in order to control the tube current, when do you have tube current? You need to have electrons. Only then, after you apply a voltage from cathode to anode, electrons will move, produce current, right. So that means the filament role is, how does it control the tube current? There is this electron. So the amount of electrons that are going to be generated here, that are ready, right, so that once the potential is applied, it can move. That is controlled by the filament circuit that you say, filament circuit. So essentially the filament circuit itself, typically you run through a 3 to 5 amperes of current at about 6 to 12 volts. But what is happening is the thin thorium tungsten wire, so that is through which the filament is made of, thoriated tungsten wire. So that is a very thin material of it is there, and when you pass this current at this voltage, due to the resistance of the wire, right, the thoriated tungsten wire, there is a drop in energy, so that it gets heated up, right. So you have what is called as thermionic emission. So ions due to thermal energy, right. So your heat is creating ions, and that is emitted out, so that it gives you free electrons. So which is called as thermionic emission. So you use this thermionic emission to get the electrons. So once you apply this, vary this, you can have the electrons ready, free electrons that are just there on the cathode side. It is created. Now the question is, I want to send it to the anode. So before we do that, we have the focusing cup. So in the cathode, you have a filament that creates this free electrons using thermionic emission, and it has its own circuitry for that. And then you have a focusing cup. Remember, the C structure that I showed you is a focusing cup. So the focusing cup helps all this electron cloud to, right, it allows this electron to go in the direction that you want, straight into the anode surface where you want to hit it. So typically it is focused to the edge, bottom edge. So that is your cathode and focusing cup. Then what happens to your, so you have what is called as primed. So at this end of this step, we say the X-ray tube is primed so that the electrons are all ready, right. Now you need to give it some kinetic energy so that it can go bombard and give you X-rays. So when you want to do that, anode is switched to high potential. What is we mean by high potential? Somewhere between 30 and 150 kilovolt P. What is this P? That is your peak. So that is the 30 to 150 kilovolt peak volt. That's what you apply, right. So this again, it has its own circuitry. You can get this voltage from the line, right, and then increase it, amplify it, rectify it, and then you can get. So you apply a very high voltage, peak voltage in the order of 130 to 150 kilovolts. So when you apply that, these part you know from the physics. So you have an anode typically made of tungsten, right. Then you have your Bremsstrahlung, you have your heat generation, collide, right. So look at this, only 1% produces Bremsstrahlung, 99% is heating. So clearly if you have this 99% heating, lot of heat is generated. So if you have a glass casing, so much of heat is generated, what is going to happen? It's just going to burst, right. It's not sustainable. So you have to cool it. So in order to cool it, that is where your anode assembly, you saw a stator and there was a rotation. In fact, there was a marking in the previous slide, right, rotator. So essentially what happens is this anode is not just a square that's static, it will rotate, right. It will rotate so that it's always, the electron is going to come and impede here. So the thickness is going to be, the electron has to go through the thickness, right. So it is going to be like this. So it is going to rotate in this direction. So we call this spins at 3200 to 3000. So there are even little more RPMs available. So it depends, I mean, that's a detail. Essentially what does it do? It dissipates heat by spinning fast so that you don't hit the same location again and again also, right. So you have the spin mechanism, that's what that rotor is for. So with respect to X-ray tube, these are the details that we need to know, where we can relate the physics of how X-ray is generated with the components that are there in X-ray tube to enable that physics. This is all we will cover, right. Again, the last but not least, when it's all housed, right. So this is a glass housing and there is a vacuum in between. So now the details are fine. So this is what the construction of a X-ray tube is. So now getting to the operational detail, because we want to use this for imaging system, what are the operational details we need to know from the instrumentation? Oh, how much X-ray to come out, right? Who has control? How do you control that? Right? That is important question. How long you want to send the X-rays? Because I don't want to fry the patient, right? Bombard him with X-rays. So how long? And is there a way to control that in the X-ray tube? Okay. So typically what we have is, we can apply this voltage, because only when you apply the voltage, the electrons come and hit and X-rays come out, right. So if the electrons don't have kinetic energy, it is not going to create X-ray. So if I have to switch off the X-ray, all I need to do is not apply this voltage, not drive this electrons to come and hit. So that is one way of thinking about it. So kilovolt peak is applied for a short duration. How is that short duration? So you can apply using a fixed timer. So you can have a control system. I mean, you can have a silicon controlled rectifier, on off switch, right. You can control that, and you can have a very good clock that has a good precision to start and stop the application of this voltage. That is one way to do it. Another way to do it is, well, I'm not in, okay, starting and stopping is good, right. I know that. So when you have a timer, I can say open the X-ray, right, apply this voltage for 0.1 second, just to use the same number that we used before, 0.1 second. What happens if it is, we'll pretend that it's all perfect, 0.1 second it does, but there is going to be some latency, right? Or because of wear and tear usage, maybe for the same 0.1 second, the amount of X-ray that comes is not same. Either it is slightly more or less depending on how you did it, right? So, you don't want that to be a parameter. You want to be extra cautious. You want to be safe because the patient safety is involved. So, I better be extra cautious. What I can do is I could have a automatic exposure control. What if this timing circuit fails? Instead of 0.1 second, somehow the rectifier got dysfunctional. Instead of 0.1 second, it goes to 1 second. It's still small time, you won't know, right? 1 second, 10 seconds. Then you are essentially frying you are bombarding the patient with so much X radiation, right? You cannot do that. So, what we could do is automatic exposure control. So, now recall the definition of exposure. Oh, we have air, amount of ionization that happens in a controlled volume of air, right? We talked about that as a exposure, the ionizing capability, right? So, here what we can do is we could have that air chamber, right? So, you could still have that. So, you can have a 5 mm thick ionizing chamber that's kept along with the patient, right? So, between your exposure. So, you could, while you think this is what you are exposing the patient, you have this calibration, you have this automatic exposure that is besides the patient, and that kind of gets a live reading of what is the ion exposure that is coming. So, if the exposure is high, then it can trigger a shutting down. So, that is based on automatic exposure control. So, you can control this based on measuring the exposure simultaneously when the patient is dosed, and that is even better, right? Because now you know, now you are not relying on just the timing, you are actually measuring and saying, okay, this is more than what this patient needs to be exposed, and so you shut it out. So, that is another way to do it. So, that is one control. The other control is tube current. So, we talked about this tube current. Tube current is important, right? Because see, this electrons that are flowing in the tube, right, that is gaining some energy and hitting, and X-rays are coming out. So, to control this tube current is important. How is this controlled? There are two aspects. One is the filament current. Why? Because the filament current creates the electrons that are ready now, right, during priming. So, the number of free electrons that are available to charge to, right, available to accelerate and share their kinetic energy with the anode to create X-rays. That is controlled, right? Tube current that can be controlled by playing with the filament current, right, because that creates the electrons available, and then of course your peak kilo electron volts. So, these two can be used to control the, so clearly if you want to produce the X-rays, it has to do with the kilo electrons. So, how many electrons, what energy it is coming and hitting, the acceleration. So, the voltage drop and the filament current which controls the free electrons available to gain this kinetic energy, both dictate your tube current. So, exposure is your tube current times how much time it is open. So, milliamperes is the current units, right, times the exposure. Exposure time is milliampere second. So, this is the reported. So, MAS is an important quantity. So, the doctors typically, or whoever is doing the data acquisition, right, they have a important role. So, they control this MAS. So, typically in the control panel, they have a control over MAS, tube current, okay, and timing. So, they can fix one or the other. Clear? Good. So, that is with respect to X-ray tube. So, now what we will do is, we finished X-ray tube configuration, we will quickly move towards filtration and restriction of X-ray photons. So, now what we have done is, first part I know, we have created this X-ray. So, when I say X-ray, just to tease you, what is coming out? anode is doing and the interaction takes place and Brahmstra lung, right. So, that remember that curve, right, the energy increases, right, then there are a lot of photons with certain energy and then it drops. So, the highest, the K peak kilovolts, kVp that you applied, right, typically there you won't get photons with that energy, right. So, you are going to have this hill kind of shape. So, that is your spectral that is coming out, polyenergetic. Okay. So, you have polyenergetic X-ray spectrum coming due to your Brahmstra lung. Now, the question is, X-ray tube has done its job, but do we want to send that to the patient directly, or is there any other physics, that aspects that we covered in the physics that we need to pay attention to? So, filtration, what do we mean by filtration? Oh, I have the spectrum that is coming out. Filter means I have to take out something, filter out something. Here what does that mean? Filter out what? X-ray photons at certain energy level. So, before we make an intuitive explanation for this, even before covering that, the need for that should come to you naturally. So, what is the need? Oh, I have this X-ray spectrum that is coming in. Can I just send it through the body? So, imaging systems, what do we want? Oh, we want signal and noise. These are what is our signal? The signal is photoelectric effect. You want to maximize the interaction. Is there a relationship with the energy and interaction? Yes. We already said, oh, if it is too little an energy, right, it will probably get absorbed in the material that it is passing through. So, we want through transmission. So, if you send low energy, right, X-rays with the lower energy, it will probably get absorbed in the body, which is very good, right. It is interacting, but then if it is completely absorbed, I won't get anything on the other side. If I say, if I spend low energy, that means everything will get absorbed here, nothing will come out on the other side. So, I won't be able to catch and say, oh, there is a differential attenuation that is distributed like that everywhere. I won't get any signal, right, every location I won't get any signal, because everything is inside of the body, it is not coming out through the other side. So, that is not, in fact, you end up dosing the patient unnecessarily. Or the other extreme, when you send the energy, high energy, oh, it does not interact. Remember our crude analogy, with all the energy I go, I just do not interact with people, I will push everybody and come through the other side. So, it will come, so you will be able to collect those X-ray photons that is coming through, the same energy. So, number of photons that you sent, pretty much you will receive the same number of photons, there will not be any attenuation, right. So, I will not be able to tell about your material. So, you need filtration, of course, we will talk about restriction. Before doing this, we know, oh, we cannot send the X-ray spectrum with all the energies, because that is not conducive for imaging perspective. So, we need to pick a range of energy where we can maximize photoelectric effect and have enough signal to have a signal to noise ratio that is appreciable, that can give you contrast. Okay. So, low energy X-rays will be absorbed by the body without providing diagnostic information. This is what we know before. So, what does filtration do? So, filtration is the process of absorbing this low energy before they enter the patient. So, X-ray tube is sending out, but before that can reach your body, I want to make sure I have some filters in place, so that I can take out all these low energy X-rays. It is better that this material that we place, the filter that we place, absorbs the low energy. You dose the material, who cares? You do not want to dose the patient, right. So, you have a material that will take all the low energy X-rays and allow only the X-ray energy that is conducive for the tissue property, so that you can get more signal and less noise, right. So, before we go into the specific filters, there are some inherent filtering also that is happening, that is without, that is the X-ray tube itself, right. So, that is within the anode and also the glass housing. This within the anode, we talked about it before I will show the plot, you will vividly appreciate the shape of the plot, right? The X-ray spectrum that is coming is like a hill. Already that time we mentioned, oh, the energies that are in the the lower end, they are generated, but the anode itself absorbs it, and so it doesn't come out of the X-ray tube. We mentioned it that time, but now probably you can convince yourself that yes, the hill shape was explained. At least on the lower end, there was a loss was explained due to inherent, right? The other is glass housing. What is the glass housing? Why is the glass housing acting as an inherent filter? Oh, because see, you are talking about high, you have tungstens, you have thermionic, so you have a lot of heat that is generated. So, some amount of vaporization happens of this material, right? So, vaporization happens, so it comes and because glass is there, it come and deposit on the glass. So, over time what happens is this there is a coating. So, there is already a coating on the glass, but over time also your vaporization, those allow a thin coating of tungsten to come and form a layer. And so, what happens? Oh, if the X-ray is generated, it has to now pass through this material before it comes out of the X-ray tube, the glass. So, low energies maybe they do not have, they will get absorbed there only. Okay. So, glass housing and within anode they act as a inherent filtering, but that is not in our control. I mean, it happens over time, it does it, but you are not proactively doing anything to it. What we proactively do is add an additional filter. So, how do I, what is happening? All I need to do is I want a material to interact with this X-ray energy and get absorbed, right. So, what you can do is aluminum is a very commonly used material for this filtering purpose. In fact, it is so common that even if you use another material, you will report the thickness of the material. See, material, when you say aluminum, you say you know the material. So, now the only aspect that determines your attenuation, what is that? E power minus mu delta x. So, thickness and the material property, your mu, together they determine the amount of attenuation. So, if I want to attenuate the signal, right, go recall our explanation on half value layer thickness and so on, right. So, that means I want a material which can absorb the X-ray energy that is coming out on the lower end, and when you mean by attenuate completely, absorb and attenuate completely, so that the other side it does not come through, it has to have minus mu delta x. So, when I say a material, it has a mu. Now, the only thing is delta x. So, that is your measure in thickness. So, equivalent thickness is always reported. So, aluminum by far is the common. So, 1-2 millimeter thick aluminum sheets are kept in front of the X-ray tube to absorb the low energy. If you do not want to use aluminum, say for example, sometimes copper is used. If you want to use copper, that is fine. You can get the equivalent thickness of copper, right, because the density, the mu is different for copper, and therefore, if it is less than aluminum, you will have a thicker copper. If it is greater than aluminum, you will have a thinner copper. But the idea is you want to filter out. So, but you report it in terms of equivalent aluminum thickness. Okay. So, this is a very common way of doing it. So, the concept is very simple, e power minus mu delta x, that is all. So, if I know my mu, whether it is copper or aluminum or whatever material, if I want my delta x needs to be changed, so that I can have how much filtering I want. If I want 90% of that energy to go down, you know what is your half value layer calculation, right, 0.693. So, you know the material, you can calculate how much thickness is required before it goes down by 50%. So, you can then say, okay, I want 90% to go. So, come up with the equivalent thickness. Okay. So, that will be used here. That is so much for filtration. In the process, what happens? I just want to spend 3 seconds on this because you know this by now. First time I showed you beam hardening was in the artifact. I said this is a little difficult to understand for now. Motion artifact is easy, detector going bad is easy, ring artifact is easy. There was a beam hardening artifact. I said maybe I'll talk about this when we get there. Maybe you will be able to explain this yourself. To top it, the previous lecture we talked about beam softening. So, can you now tell to yourself what is beam hardening? What do you expect beam hardening to be? Oh, so I have beam, which is the X-ray energy that is going in, right? That the hill that we talked about. So, now what have you done because of filtering? I am basically taking out the lower end of the spectrum, right? I am taking the lower end of the spectrum. So, now what will happen to the mean energy that is coming out? So, if you have the hill, there is a mean value, right? If I preferentially take the low side, now I take the mean, what is going to happen? The mean energy level is going to be higher than before, right? Because the low energy photons are removed. So, you have so many photons, but all of them are on the higher energy side. So, the average of that is going to be greater than when you had low and high and having an average. It is going to be skewed, right. So, you are going to have higher. So, that means beam energy is increased. The average beam energy of the spectrum that is coming out after filtration is increased, hardened, right. When it was decreasing, where did it decrease? It is called beam softening. Go check back where we talked about beam softening. It was last lecture or the previous one. The energy was reduced, the average energy was reduced, it was moving towards the left. That was softening. This is hardening. Okay. So, this can happen not just by the filter that you are putting. It happens, it could happen also within the body. So, if you have layers where suddenly you have a layer that absorbs way more than, right, the neighbor or the front or back, right, neighbor in the depth direction or front or back, then what is going to happen? There is going to be a beam hardening. So, you are sending the spectrum, I hit a very high, so I have a, just for argument, okay, not natural, just for argument, there is a bullet, there is an implant, there is a metal, something is there, right. So, if I go, there is a rapid, right, there is going to be a different, there is going to be more absorption. And so, the spectrum that is in front of that metal and the spectrum that is coming out of the metal to probe through the other tissues are different, right. The beam is hardened after going through that material, right. So, you could get beam hardening artifact because of these things. Okay. So, you know where it is coming from. It is due to filtration effect. We have mostly listed filtration from the outside, but it can also happen inside depending on the material. Okay. So much is good. So, this is fine for filtration with respect to energy. What is restriction? Oh, I go for a chest X-ray, right. I go for a chest X-ray. I better get only my chest exposed. I don't want my head, right, arms, legs. Why should that get exposed? Why should I do? I am not interested in imaging that. Why should give dose to that? So, restriction is going to be essentially just before going to restriction, let us just complete this. I told visually just to spoil your imagination, right. This is the same thing that we saw before, the hill. What is new in this is, the previous time we saw this hill, we had different kilo electron volts. So, there were several hills, but each one was for different applied voltage. Whereas, here you see different hills, not because of that. You see different hills or the spectrum after each process that we have covered so far. So, this is your theoretical. Bremsstraw lung creates X-rays within the anode starting from 0 energy till whatever maximum you have applied, kilo electron volt, right. So, However, because, so this is what is actually generated. However, before it can leave the anode, the low energy, right, these things are absorbed by the anode itself, right. So, progressively what is leaving the anode is not having low energy. In fact, number of photons with low energy is less, and only X-ray photons that have higher energies are leaving the anode, right. So, this is at the anode. But then after anode we talked about internal filtering, right. So, you have the X-ray tube. So, this is the one that is leaving the tube. So, this already less, lower energies are filtered due to the intrinsic factors, right. So, this is the shape of the energy spectra that is coming out. Now, we have added the filter. Okay, so when we added the filter, again we have shaved off, filtered off low energy. So, we are preferentially giving only from 30. It starts with there about 20, 30. It goes up and then it goes down. And then this is a leaving body. So, that means it is going into the body. This is the spectrum that is after the filtration. This spectrum is going inside the body. Inside the body, obviously we are interested in attenuation, right, interaction. We are talking about a mu. If it is completely 0, then there is no use. That is the whole idea. We try to remove the low energy. We need to get a spectrum outside the body. Otherwise, everything is lost inside the body. So, once we sent 30 to actually 100 is just for writing purposes, but there are very less photons, right. So, when you have 30 to 100 kilo electron distribution that is sent, what is leaving the body? Only this is leaving the body, about 50 to 100, right. So, so you can see there is a differential attenuation, that is what is exploited to see in the body. So, we have different mu's in different regions, different tissues. So, I send this spectrum, it leaves that spectrum. So, you get some signal in these energies. So, based on this we need to talk about what was the attenuation distribution in the body. So, you see the energy, how it is changing. So, that is why I said this plot is a very important plot, because it kind of tells the summary of what is the signal, what is the signal quantity and the range that you are talking about in X-ray physics for imaging purpose. Okay, fine. So, now we will just quickly talk about restriction. Restriction is essentially to, all this is fine with respect to energy and how it goes in, the filtration is fine, but then if I go for a chest X-ray, I better send the X-ray only through the chest. What is the point in sending through the head or arms or legs, right? That is the logic. So, what can you do to restrict it? The same logic is, so for example, let me try this. I do not know how well it will come. I have a torch, right? So okay, so I do not know how clear it is, but then okay, so let me try this, right. So, I get a so I have a field of view, right. I am trying to hit my pocket, right. I want to hit my pocket or more microphone, right. I want to do this, but then microphone is so small. Why should I hit everywhere else? So, what I can do? I can, right, filter everything out, but then have a small opening. I have a small opening that will exactly allow me to shed light on the microphone only, right. Why should I illuminate? The field of view from this is wider, right. It is wider than the microphone that I want to illuminate. So, why should I illuminate the other regions? What I can do is restrict it. So, I can attenuate the other regions and have a small opening so that only the field of view is illuminated, right. So it doesn't come out well here, because it's so usually I do this in the class. We have a overhead project, you have a projector, so it is actually a through transmission. So I could try this, play with this, but unfortunately here I have a camera system. It's not through transmission. So when I try to do this, my object is blocking the camera side of it. The detector is on the front side, right. So but I guess you can, this fairly intuitive, that you can try it yourself as well. You can try it yourself as well to get the big picture. Okay. So essentially what we talked about is X-ray tube. It is coming out. Usually it comes like a cone, right. All directions. Source is a small region. So when it comes out, it opens up in all directions like this. So it will be like a cone that when it comes out. So you can have a diaphragm beam restrictor. What is a diaphragm beam restrictor? Essentially the example that I showed. You can have a lead or whatever sheet where you have a small opening. So rest of the places it will get absorbed. Only the opening will allow the restricted field of view. So this would be your field of view otherwise. Now by introducing this, I have a small opening, only the field of view is restricted. The rest of the places it will be absorbed, right. So that is very simple, straightforward, but the challenge or the limitation is you can have only one size, right. It's very custom. Likewise, you could have a cone beam restrictor. So you could have a cone shaped, right. So you can move this front or back. So it has some advantage compared to diaphragm, but still the most popular one is your collimator beam restrictor. You have two of them. So you can actually adjust the slit size, the opening, and you can also adjust the front back, so that you can change the field of view, right, in a more flexible fashion. The concept is same. Again, this aperture is opening, the rest of the material will absorb and not allowed to go. So the opening is fixed here. Here you have opening that can be adjusted. Not only that, you have two of them, that gives you little more flexibility. So I can, in a graded fashion, I can do, right. So this gives you little more flexibility. By far this is the most common restrictor, right, collimator. So this term collimator we did briefly mention, but we will talk about this even more when we talk about the detector side of it. Collimator means it's sending in one direction. It gives you the direction, the field of view, right, where you want. It is able to direct it in that direction. So we will stop here. We have covered filtration and restriction. The next part is going to be your source side is almost done, right. X-ray tube, filter. So you are ready now to send this to the exact field of view you want, with the exact energy that is likely to give you a good interaction and good signal. We are ready. Now, is there anything to do with the patient, or can we just talk about detector, right? We are talking about instrumentation. So there is one little step that you can still do before you get to the detector details with respect to customizing it for the patient, which is what we will do. So customizing it for the patient, the instrumentation that is used to customize based on the patient, and the detector side we will cover in the next lecture. So far we have covered the instrumentation on the source subsystem. The next lecture we will cover the remaining part, and that will complete the instrumentation aspect that we wanted to cover. Thank you.